Chapter 8 is on series solutions to differential equations. So this will be a little review at first regarding basically the concepts we would have seen in Calc 2 or integral calculus, 65A or 65B at Chaffee. So first, let's review everything that's written down here, which is the Taylor polynomial or Taylor approximation. So this is the Taylor polynomial used to approximate a function. So basically, it's around a specific point, like 0 or whatever, pi, and as you extend the approximation indefinitely, like as it approaches infinity, then you get exact values as you take a limit type of thing. So you take your function, whatever it may be, and you can reference stuff down here. Just suppose it's like sine or e or something, and that's your function value. And then if you evaluate at a point, then that's what you get next. You get that value, and then you can get exact values if you approach infinity around that value. So you evaluate f, you do the derivative. Oh, and then so f is in derivatives, right? And then if it doesn't, then you can still get an approximation. It's just not an exact value as you take a limit. And we'll talk about convergence and things like that. So you take the derivative, evaluate, and then you do the difference. So here's where you're getting your actual like the variable you're putting in. So here's your variable. We can highlight this. So here's your variable here, and then these are your variables. The rest are your specific values as you evaluate. Okay, so that's your x. And then you do second derivative divided by 2 factorial, and then you do the difference squared, and you keep going that pattern. So this is 3 and then 3 factorial, so third derivative, and then you keep going. So it's the nth derivative evaluated at x naught, n factorial times x minus x naught to the n. So all those match. So this and this and this all match. And then here's your general form. And then you get theorems and other things that say when there's convergence, that says you take a limit as n approaches infinity, then you get the exact function. Right? You get the exact function of whatever that is. So here's some examples of those down here. We don't look so much at probably tan and hyperbolic sine or cosine, but this was just something from a different book I threw in to kind of give you the idea. And it gives you the intervals of convergence on the side. You may recall a Maclaurin series is basically the simplified version of Taylor. So Maclaurin series is centered at a point. Centered at 0. The point that it's centered on is 0. I believe in some other books they use a C. It doesn't really matter, of course, but you can say C is 0, or this ends up being a C value right there. And so, e to the x, sine x, cosine x, natural log, those are all the typical expansions of the Taylor polynomial. And we're going to look next at how to use it to approximate a solution to a differential equation. So let's look at that. That's what I want to get to. This is what would be different than what you've done before. So let's look at this example. And I'll say construct and this will be a Taylor series centered at 0. So I'm just going to call it a Maclaurin series. So construct a Maclaurin series. And of course that means x naught is 0 for Taylor. For the initial value problem, given here. So y double prime is equal to 3y prime plus x squared y. Initial conditions, y of 0 is 10, y prime of 0 is 5. And so we'll be able to use these in our Taylor expansion. So we're going to be using this exact form to expand, and we'll be given those first couple terms. Then it's up to us to find the other terms given these terms back into this function. So let's write down our Taylor polynomial. So and we could copy this, but I'll assume we're all writing in pencil or something. So P sub n is equal to y of 0 plus y prime of 0. And that would be like, it's really over like 0 factorial, and this is actually over 1 factorial, which is still just 1. And then x minus 0 is just x. And then plus y double prime of 0 over 2 factorial x squared. And so that normally would be your x minus 0 squared, right? Here and here is x minus 0. And then x minus 0, and then you'd square it. But at 0, of course, like, okay. Plus y triple prime of 0 over 3 factorial x cubed, and then we can write our standard form is y in nth derivative of 0 over n factorial x to the n. Okay, so now we basically will calculate values for those. This, I forget how many values or terms it said to use, but we'll figure that out. Yeah, I don't think it really said. We'll do, I think they do 5 terms on this one. Okay, we'll just do that. Okay, so we need to calculate. So we need values for y of 0, which is, well, actually that's given, but we'll just say we need that value. And then y prime of 0, which is given. And then this is what we have to calculate. Y double prime of 0, y triple prime of 0, etc. So we need to expand that out and calculate it. So we're actually given those terms. So this y of 0 is actually 10, and then y prime of 0 is actually 5. And so then we will calculate the others. Okay. All right, so to calculate y double prime of 0, we can use the given equation. Okay, so we're going to use that given equation to actually do that calculation, right? We're going to use that. So what we get is y double prime of 0 is equal to 3 times y prime of 0. Those are actually, functions of something. And then plus 0 squared y of 0. Let me fix that. Hold on. Too many parentheses in there. 0 squared y of 0, which is just 0, of course. So that's 3 times, and we know y prime of 0 is 5. So you say 3 times 5, and then plus 0. I'll just put it in for now. So you get 15. So now we know what y double prime is. Now we want to keep going. Right, to find the higher orders, we differentiate both sides. So I'll just say now differentiate both sides to find higher order. So we let's just start with what's given. So write this down. I'll just copy this thing. So we start with that. And then I'll just differentiate both sides. We'll go across like this. So that implies you get y triple prime equal to, and then now like you'll have to use product rule here, right? You have to use product rule. You'll have to use whatever happens, right? You'll get 2x, but then you gotta do y is 1 and then y prime, but you got to use the product rule when you differentiate that. So it's not like a partial. It's like it's more like implicit. So y triple prime equals 3 y double prime. You just take the derivative again of that, and then plus derivative of the first times the second, plus the first times the derivative of the second, and then times the y prime. But we know what those values are when we evaluate. But we're going to need, they went up to, I think, 5 on this one, so we'll do the same. So we continue y to the fourth is equal to, and then take this next derivative, so it's y triple prime plus 2y plus 2x y prime plus 2x y prime. Again, so you'll have 4 of those, plus x squared y double prime. Then we can simplify that. That's 3 y triple prime plus 2y plus 4x y prime, I'm running out of room here, plus x squared y double prime. And then do the derivative again. Fifth derivative is equal to 3y, 4, not 5, plus 2y prime plus 4y prime plus 4x y double prime plus 2x y double prime plus x squared y triple prime. And then simplify that. I'll just come down here. Okay, so combine that together. 3y to the fourth prime, that is 6y prime plus 6xy double prime plus x squared y triple prime. All right, so you're just combining and you're doing product rules on those, and then now you have to evaluate. Okay, so now evaluate for or with x equal to 0. So we got to do that calculation. So you get y triple prime of 0 is 3 times 15, and the rest are zeros, so you get 45. Oops, no, I gotta do 4 to the fourth derivative of 0, so you get 3 times 45. And then you get plus 2 times 10, and the rest zeros, so it's 155. Y to the fifth power, no, fifth derivative. 3 times 155 plus 6 times 5 equals 495. Okay, so now you can use that in the expansion and get your p sub 5, basically. So now substituting back into here, we get our Maclaurin series or polynomial. Actually has 6 terms, but so p sub 5 of x then is equal to 10 plus 5x, and then 15 is what we calculated, 2 factorial x squared plus 45 over 3 factorial x cubed plus 155 over 4 factorial x to the 4th plus 495 over 5 factorial x to the 5th. Okay, and then we can just reduce that. So 10 plus 5x, that doesn't change. That doesn't change. That's just 5 halves x squared plus, then you get 45 over 6, so you get 5 reduces, so that's just again 15 halves cubed plus and then 4 factorial is 4, 3, 2, 1. Nothing goes into 155, so that's just 24 and then 4, and you'll trust me that reduces to 33/8. All right, so there's your Taylor approximation, which is a Maclaurin series centered at 0 for that initial value problem. So that would be the solution to it. So it is approximation though, because we stopped. Like these don't really converge or be exact unless you say plus dot 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 and has that infinite sum. But it can be very useful for other purposes. Okay, let's do another example. So this is number 2 in the book, 8.1. This will be a little easier. So determine the first 3 non-zero terms of the Taylor polynomial. So it's a Maclaurin series centered at 0. And so we're given y prime is equal to y squared. And our initial conditions, y of 0 is equal to 2. So it's the same process, basically, to do the same thing. And we want to find that Taylor expansion. So I was going to copy that same thing. So this is what we're doing. Like if you want to copy a formula down, that's your formula. And we'll do the same process. So this is a good place to just try it. Nothing real new. Figured I'd do one that's homework. All right, so we're going to simplify that. We're already given that this is 2, so that's where you'll put 2 right there. And then we got to evaluate to find the next few terms, right? Just like before. So we'll just evaluate. So y prime of 0 is equal to y of 0 squared. So that's just going to be 2 squared is equal to 4. Well, that's simple enough. And then y double prime, we'll have to calculate, is equal to, well, that's just 2y y prime using the chain rule. Or, yeah, chain rule. 2, so that's just 2y. So y prime is y squared. So it's just 2y y squared, which is equal to 2y cubed. Okay, so then we can evaluate y double prime at 0. Calculate that. That's 2 times y of 0 cubed. So that's equal to 2 times 2 cubed, which is 16. And we can do y triple prime. So y triple prime is equal to 6y squared times y prime, right? Just taking the derivative and then using the chain rule. So that's just 6y squared, but y prime is y squared. So that's 6y to the 4th. And then we can evaluate y triple prime at 0. You get 6y of 0, and then what was that? To the 4th. So it's 6 times, and that'll be y of 0 was 2, so it's 2 to the 4th. So it's 6 times 16, which is 96. Therefore, our p sub n of x is equal to, and now we can just substitute in the values. So that's just going to be 2 plus 4x plus, and then that'll be, what was y? 16 over 2, so that's 8 x squared plus, and then what is going to be 96 over 6, so that reduces to 16. So that 6 actually just reduces right there. So it's 16x cubed. Okay, dot, dot, dot. So I did, I think, one more term. So 1, 2, 3, 4. I actually did 4 terms. They just said to do 3 terms. I did 1 extra. But that's the process you go through. Okay, 8.2 is a review of power series. And then we'll get on to solutions again and of differential equations in 8.3. Okay, so there we go.